with our problem, we have to talk a little bit about Avogadro's law. And to do this, we're going to assume that our gas in our graduated cylinder was an ideal gas, which means that we're going to assume that this gas obeys all laws of the kinetic molecular theory. So we're looking at Avogadro's law. Equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Doubling the number of moles of gas doubles its volume, as long as we don't change the temperature and pressure. So hopefully from that statement you can deduce that relationship between moles of a gas and volume of a gas is going to be a directly proportional relationship. Since it's directly proportional, I can look at this relationship. Using N to represent the number of moles, B, volume of a gas, I can use this relationship to proceed on. Directly proportional between moles of a gas and volume of a gas. Okay? Now remember, when I'm looking at these directly proportional relationships, I can look at these ratios this way, I can look at them this way, depending on what my variable is. Remember, sometimes we get confused if our unknown is in the denominator. So I may want to write this depending on what my unknown is. Okay, using Avogadro's law to determine the number of moles of butane gas. Assume butane is ideal and that 1 mole has a volume of 22.4 liters. Okay, so here's going to be our V1 and our N1 and V1. 1 mole, 22.4 liters. N and V. Okay, so I'm going to be looking at this relationship. N1, V1 equals N2, V2. Because my N is going to be my unknown. So, rearranging here, we have N1, V2 over V1 is going to equal N2. My V2, go back to question number 10, volume of the butane at STP. Okay, so I've got 1 mole, whoops, what happened there? 1 mole, and V2, that was my volume, 0.0890 liters, divided by 22.4 liters is going to give me the number of moles that I would have of that gas at STP. Dividing that out, you should get 0.00397 moles. Okay. Now, experimentally, how many grams? Okay, grams per mole is molar mass. So, go back to question number 6, mass of butane collected. We had 0.18 grams over 0.00397 moles. Dividing is going to give us 45 grams per mole, which is a much better value than the 135 grams per mole we had on the run we did in class. Okay, now, molecular formula of butane, C4H10. Calculate its molar mass. How do I do that? Look at the formula. 4 carbons plus 10 hydrogens will give you the molar mass of butane. Looking at, get this out of the way, percent error using the accepted molar mass of butane. And finally, 15, discuss any sources of error. Okay, so talk about sources of error in the beginning. We'll compare the data we collected fourth period and the data we collected after school today. Compare those two. Talk about the potential sources of error for this. And see if we cleaned up maybe a little bit of this.